Hello students, welcome to AdiChemistry's online coaching. This presentation is a concise introduction to Jahn-Teller Effect and is designed for advanced level students appearing for university level examinations in chemistry. Don't hesitate to raise any questions or seek clarification on any points during the lecture that you are not clear about. My name is Aditya Vardhan, creator of adichemistry.com from Warangal. Now let us delve into the topic. It is observed that certain octahedral complexes with partially filled degenerate orbitals, particularly those involving the cupric ion, exhibit a notable deviation from the ideal octahedral geometry. Instead of maintaining perfect octahedral geometry, these complexes often undergo distortion, resulting in a less symmetrical tetragonal geometry. There may be elongation of two bonds on a particular axis leading to tetragonal geometry, or there may be compression again leading to tetragonal configuration. By considering the elongation or compression occurs on z-axis, the first one is referred to as z-out distortion, while the second one is referred to as z-in distortion. This distortion is commonly referred to as the Jahn-Teller effect. It is not only restricted to octahedral complexes but is also observed in other nonlinear molecules such as tetrahedral complexes. This effect was first proposed by physicists Hermann Jahn and Edward Teller in 1937. According to them, in an electronically degenerate state, a nonlinear molecule undergoes distortion to eliminate the degeneracy, thereby reducing both symmetry and energy. This is known as Jahn-Teller theorem. One should keep in mind that Jahn-Teller distortion is observed in case of electronically degenerate systems only. Now let us see what is an electronically degenerate state. It represents the availability of more than one degenerate orbitals for an electron. In this condition, the degenerate orbitals are said to be asymmetrically occupied and are associated with more energy. One should recall that degenerate orbitals are associated with same amount of energy. Let us now try to understand the degeneracy using examples. The first example is D1 configuration in octahedral environment. In presence of ligands, the d orbitals undergo crystal field splitting as shown on the screen. Since the ligands approach along the x, y and z axis, the dx square minus y square and dz square orbitals experience greater repulsion as their lobes are oriented along the axis. As a result, these orbitals are raised in energy and together form the EZ set. The remaining orbitals dxy, dxz and dyz are lowered in energy since their lobes are oriented in between the axes and hence experience less repulsion. These orbitals constitute the T2G set. In a D1 system, the single electron occupies one of the T2G orbitals as shown on the screen. Since all the three T2G orbitals are degenerate and are associated with same energy, there are three equivalent ways to place the single electron, and this condition is referred to as electronically degenerate state, and the system is associated with higher energy. To lower the energy, the system may undergo distortion, reducing both symmetry and degeneracy, which is otherwise known as the Jahn-Teller effect. Now let us go through D3 electronic configuration in octahedral environment. In this case, all the degenerate orbitals of T2G set are occupied. Only one configuration is possible, hence it is said to be electronically non-degenerate. It does not show Jahn-Teller distortion. Now let us consider the third example. A metal ion with a D9 configuration in an octahedral field is electronically degenerate because there are two possible ways to arrange the 3 electrons in the doubly degenerate EG set. As already stated, this degeneracy creates instability and the metal ion with D9 configuration tends to undergo Jahn-Teller distortion to lower its energy. The best example is cupric ion. Now let us examine what happens during the distortion. In the case of Z-out Jahn-Teller distortion, the bonds along the Z-axis elongate. This reduces the repulsion between the ligands and the d orbitals that have a Z component. Consequently, the dz2, dxz and dyz orbitals experience a decrease in energy as shown on the screen. The 9th electron now occupies the dx2 minus y2 orbital, which is no longer degenerate. Thus, the electronic degeneracy is lifted and the system stabilizes. However, this stabilization comes with a loss of symmetry in the complex. Now let us see what happens in the case of Z in distortion. The bonds along the Z axis become shorter. Because of this, the d orbitals that have a Z component come closer to the ligands and experience more repulsion. Therefore, the dz2, dxz and dyz orbitals go up in energy as shown on the screen. The 9th electron now occupies dz2 orbital, which is no longer degenerate, and hence the system stabilizes. Again, the stabilization comes with a loss of symmetry in the complex. You can observe both in Z out and Z in distortions, the perfectly symmetrical octahedral complex becomes tetragonal. Let us sum up what we have learned up to now. In an electronically degenerate state, the orbitals are asymmetrically occupied and hence are associated with higher energy. Therefore, the system tries to get rid of excess energy by lowering the overall symmetry of the molecule, and this is known as Jahn-Teller distortion. That's all for now. Visit AdiChemistry.com for more information on this topic or search for AdiChemistry Jahn-Teller Effect by using any search engine. Don't forget to like, share and subscribe.